Hello, my name is Paul Griffin. I'm a lecturer in experimental physics at the University of Strathclyde, and I'm going to talk today about a subject called quantum technologies. Now, this is a very exciting field right now. You're at a quantum technology school, so you clearly recognize it, and I'm lucky enough to work with a number of excellent young and older researchers who are interested in quantum technology and ultimately shining lasers at things. We're going to kick off with a quiz. 3 things in order of increasing maybe complexity, but which of them rely on quantum physics? Is it a fridge magnet? Is it a sat nav? Or is it an MRI brain scanner? Think about it, and we're going to come back to it later in the discussion where we'll dig in a little bit more. So we're going to take off from here with a history lesson. So about 120 years ago, Lord Kelvin, the most famous scientist of the time, looked back on the developments of Newton and of electromagnetic radiation and realized that we understood an awful lot of physics, and was reputed to have said there is nothing new to be discovered in physics now. And there's a problem, and the problem was a light bulb. You pass electricity through a filament, it glows white, and you know that a white object has got a spectrum. It's got an amount of blue light, an amount of green light, an amount of red light with increasing wavelength. We can see this in nature. If you have a beautiful rainbow, it automatically blends these or separates these colors out using dispersion and refraction, and to give us the colors from Roy Gibbov or wherever you like to remember it. In a lab, we don't generally have rainbows. We're not allowed to spray water around, so we use a prism instead, and you shine white light into a prism. It splits into different colors. And the theory at the time said if we look at the different frequencies, so if we start at red and go down to increasing frequency, shorter and shorter wavelengths, how much energy do I have at those different frequencies? And the theory had this simple shape which said as you went to higher frequencies, you got more and more energy. And the experiments, which were very carefully done, disagreed. So this scientist, Paul Ehrenfest, one of the most intelligent scientists of the time, described this as a catastrophe, very dramatically. Actually, he called it an ultraviolet catastrophe, because everything worked really well until we got to the ultraviolet part of the spectrum and things fell apart. How do we figure out the answer to this? Well, Max Planck, another famous scientist, he pondered this, and he did what I'm sure you have done, which I definitely have done, is when you have a problem, you open your book and look at the back and see if the answer is in there. And he looked at the experimental results, and the only way he could figure out to make the experiment and theory match was to say that light, instead of being emitted as a continuous set of waves, was emitted as chunks. So in blue light, if I wanted to make more blue light, I could just have to give out another bigger chunk of blue light, or if I want red light, I can only emit it in certain amounts of chunks. He called this, again dramatically, an act of despair. But whether it was an act of despair or not, the theory and the experiment matched perfectly, which meant that there had to be a nugget of wisdom in there. And the essence of what Planck said was that the energy of a system was given in multiples of n, was going to be given by this equation n times h times f, where energy was some integer times this constant h, which is Planck's constant times the frequency. And Planck's constant is a very, very small number, 6.6 times 10 to the minus 34 joules. What this is interesting is that if you and I look at an oscillator, and to me a simple swing in a playground is the simplest oscillator you can think of, that swings back and forth. The equations we have for that are E equals a half mv squared, where we map the velocity at any particular time. But we don't see these quantum effects. So in everyday physics, we're not seeing these quantum effects, but as a scale of individual atoms and photons, it starts to come out. The next person we're going to meet in our little journey is Einstein. And Einstein won the Nobel Prize, same as Ehrenfest and Planck. A lot of people think that Einstein won the Nobel Prize for E equals mc squared. He didn't. He won the Nobel Prize for proving Planck's theory. This equation, which says that the energy of a photon was given, or the energy of a photon emitted was given by h times f, with this extra factor in here, which is to do with the nature of metals. And he proves that light indeed is emitted in chunks, which are called quanta. Quanta is a Greek word, or a Greek origin word that means packets. So light is emitted in packets. And this is strange. You and I know that there's things like waves, and there's waves and particles. Waves are like a motion on a string, or water waves, and particles are solid things like a ball. Waves show things like interference, and balls show things like they move like trajectories. And one of the things that came out of what Einstein was saying was that, or Planck was saying, and Einstein backed up, was that light is a wave, but it also is a particle. This crazy idea that we have to think about this wave-particle duality. Not many people were a big fan of it at the time, but they still researched it and found out where this interesting idea would take them. An example that I like when we look into this is looking at the Thomson family. There's J.J. Thomson and his son George Thomson. J.J. Thomson won a Nobel Prize in 1906 for proving the electron as a particle, and his son, 31 years later, won it for proving the electron as a wave. And that work for George Thomson was done at Aberdeen, so it's a nice link back to our Scottish quantum technology adventure. So let's go back to Einstein. Einstein pondered all this evidence coming through of being waves and particles, and he took the brave thing to say, we're not actually thinking about the same. It's a new kind of difficulty we have to think about. We have two contradictory pictures of reality, and separately, neither of them fully explains the phenomena of light, but together they do. He said, we don't like it, but we have to accept that light is both a wave and a particle. 1927, there was this big meeting in a place called Solvay. 29 people attended, 17 of those got Nobel Prizes. A number of famous people like Erwin Schrödinger, who hated this idea of quantum mechanics. He said some of the ideas of wave-particle duality were as kin to thinking of a box where you had a cat inside, and if you did some probabilistic measurement, the cat was not alive or dead, it was both alive and dead at the same time. He hated it. Wolfgang Pauli, who said two electrons cannot be in the same place at the same time. It's forbidden. Heisenberg said you can't know how fast you're going and where you are at the same time. Niels Bohr came up with this entire picture of the atom being somehow like a solar system, and the electrons could only be in certain positions but not in between. Of course, Einstein we've met beforehand, and for me the most interesting is Marie Skłodowska-Curie. And she's very interesting because she discovered radioactivity, discovered the elements radium and polonium, invented radiotherapy, and was the first person to win 2 Nobel Prizes, and she also won Nobel Prizes in different fields. Out of these kind of meetings, though, this idea of quantum physics came around, and quantum physics basically describes the behavior and interactions of fundamental components of nature, atoms, photons, and the stuff that they are made of. And things that have come from quantum physics in the time are developments that we did not know about in 1927 are semiconductors. So things like your phones and your laptops, and lasers, which drive things like simple as your barcode checkout and on the way to the whole internet. Other things quantum mechanics have done, and all of these actually are quantum physics, from the level of a magnetic resonance imager, which relies on the fact that we can control nuclei in your brain, to sat-nav, which uses atomic clocks in space, and fridge magnets. The way magnets work is fundamentally a quantum physics, and it's extremely complicated quantum physics. But the nice thing about it is it works. Now my work, as I said at the start, I'm an experimental atomic physicist, and I use atoms. So we get the whole periodic table on here, and why we like using atoms is if we want to pick a particular atom, say hydrogen on the top left, 2 hydrogen atoms are always going to be made of the same thing. They're going to have the same mass, they're going to have the same components, protons, electrons, and allows us to do fundamental experiments. What kind of experiments we can do? Well, we can measure the properties of atoms. That's how quantum mechanics kind of came around, as people asking these kind of questions. We can also measure the effect of things in atoms. We can measure the force of gravity, how it changes the way the atoms behave, how magnetic fields. We can start trying to build up new technologies rather than making things smaller, make things bigger, one atom at a time. And we can also look at interesting physics. And the kind of interesting physics we can look at, it comes into the idea of superposition. So in computers, we have things like ones and zeros. In a switch, you can have it on or off, the light in your room. And atoms have different energy levels, and you can have an electron in an energy level close to the nucleus, which is higher, more tightly bound, and an electron further away. But in contrast to light switches and to ones and zeros, an atom can be in a superposition of excited and ground state at the same time, which you cannot get from a light switch or from a 1 and a 0. And this is interesting because it now allows us to do experiments where we can make a superposition of a cat being alive and dead without having to kill and maim any cats. We can also do more exotic experiments, like a cat being on holidays and not on holidays, 2 atoms being in different places at the same time. Look at exotic superpositions. And this we do these in the labs all the time. So how do we use atoms? Again, a little bit of history. This is a comet, picture of a comet from a couple of years ago, and there was and the comet has this beautiful tail, the streams behind it. And the picture I always had of a comet tail was that it's like if you have more hair than I do and you're going down a hill on your bike, your hair is going to stream behind you. And what Kepler noticed in the 17th century was that the comet tail always points away from the sun. And he said that there might be some pressure coming off the sun, maybe even a pressure of light. And Maxwell, another great Scottish scientist, said, well, actually the pressure comes from electromagnetic fields. The fact light itself, even though light has no mass, it can exert a pressure and a force. And so we take that idea, we say, how do we exert effects on atoms? Well, we use lasers, the cleanest, most coherent source of light we can get. And the normal picture of a laser hitting something is that it's destructive. We do it in very gentle ways so that we can precisely and exquisitely control the behavior of the atom. And we do this to examine the nature of quantum phenomena. Like I said, look at Schrodinger's cat. Experiments these ideas of superpositions, of atoms being in two places at the same time. Look at an entanglement, that atoms that are far apart can interact with each other faster than the speed of light. This was an idea that it was so shocking at the time that it made the front page of the New York Times. The idea was that Einstein attacks quantum theory. The subheading, I think, is a fantastic idea of how to phrase an insult. Einstein, scientists and his two colleagues said it is not complete, even though it is correct. Which, it's a quite subtle dig, I think. And we can also look at things like wave-particle duality, where when particles are in the classical regime moving around us, that they behave like particles, they've got positions and trajectories, and as they get colder and colder, they start behaving more like waves. And so for temperature, we're probably familiar with Fahrenheit and Celsius, hopefully just Celsius, where 0 is the freezing point of water and 100 is the boiling point of water. But Kelvin, how we met at the very start, he pointed out that if you look at this scale of looking at the energies of atoms or molecules, there's a minimum temperature we can get to called absolute zero, which is minus 273.15 degrees centigrade. And so rather than using such a weird number, let's just call that one 0 and scale up. And so the scales of these temperatures we can think about are on a log scale, where we're looking at powers of 10 as we're going down, looking at the center of the sun, the surface of the sun, Glasgow on a hot day, Glasgow on a cold day, liquid helium, the coldest thing that was known at the time of Kelvin. We need to go many, many times colder in order to see quantum effects. We're getting down here into the regime of nanokelvins in order to see these quantum effects that we're interested in. How do we do that? Well, we build up these experiments. We use vacuum chambers, we use lasers, we have lots of electronics, and we've got people that work in a lab. And in this process, we can make, in this red blob that's here, is 1 billion atoms that are cooled down to about 1/1000th of a degree above absolute zero. And when these atoms are so cold, we can do interesting things with them. This was the picture I showed you beforehand about wave-particle duality, is that we have these waves, they're coming from double slits, they propagate along and we see this nice wave interference pattern, but when you look at it, photons are arriving one at a time. On the right hand side is a picture we took in our lab, which is we made two clouds of atoms and we made them interfere with each other. We made them show this wave, atoms behave like waves, but we can also show they behave like particles, and it's the exact same image that we're looking at, the same type of image we're looking at the left and the right, looking at the wave-particle duality of photons and of atoms. So that brings us on to quantum technologies. Quantum technologies are any technologies that exploit quantum physics. This is a massively growing field, so we're going back 40 years. You can see that this is when it first became proposed, around the year 2000, it took off, and in the last 5 years it's exploded, become a huge area. And this is the frequency of which papers are published. And quantum technology itself is a field of engineering and physics, and it translates the ideas of quantum physics into practical applications. It tries to do real things that have this disruptive potential, could completely change the way that we work and live in society. And the idea is that we can control these quantum entities, and if we can utilize their characteristics, like entanglement and superpositions, we can make new sensors, new types of computers, new cryptography, new technologies entirely. And there's entirely new journals that are looking at advanced quantum technologies. And now, why now? Well, if you look back to Schrodinger, the guy who came up with the cat picture that we may not or may not like, at the time, even though he didn't like quantum mechanics, he basically wrote an awful lot of the theory of it, but he also said quantum mechanics is a lovely theory, but it's not practical. He said it's fair to state that we are not experimenting with single particles any more than we can raise an ichthyosaur in a zoo. An ichthyosaur, here's a picture I took from the Natural History Museum website. It's I'm going to call it a dinosaur. I'm sure some of you will disagree, but it was a dinosaur-like animal that lived in the water. So he says we cannot interact with single particles or single photons. And I hate to say we can. We've got to now to the point where technology is developed that we can do these experiments. So this is my colleague Jonathan Pritchard, who has a lab beside mine, and he works in this project called Square, where he traps single atoms. Not only can he trap single atoms, he can trap these single atoms and put them at particular points in space so that he can make what's called a quantum register or a quantum computer. And quantum computing is becoming a reality. People are building quantum computers and actually starting to sell quantum computers, and some of these are being built in Glasgow and in Edinburgh and throughout Scotland. And Scotland is one of the leading countries that are looking at quantum technologies and quantum computing. We'll come back to quantum computing in a little bit, but the kind of quantum technologies we're looking at are quantum measurement. Can we measure time more accurately? Can we quantum sensing? Can we measure magnetic fields? Can we get secure quantum communications? Does even the nature of information change? And can we start doing quantum enhanced imaging? So quantum computers use these ideas of superpositions to make, you've probably heard about it in some news, but Bill Phillips, who won a Nobel Prize in 1997, said it's kind of crazy to start talking about quantum computers in relation to modern computers, because quantum computers are as different from today's digital computers as today's computers are from an abacus. And when you were sitting at home when you were 3 playing around with an abacus, I'm sure you weren't thinking about what you can do with Candy Crush on your phone. Right? There's that level of abstraction what quantum computers will be able to do, whether it's solving problems of traffic flow or making new chemistry from protein folding or different areas. It's just revolutionary. Quantum sensing, as I mentioned before, GPS uses accurate clocks in space. We can make more and more accurate clocks, which means that we can position ourselves down to centimeter resolution, which has, you know, even a simple thing of engineering, looking at road subsidence or driverless cars. We can make new types of brain scanners, and with this quantum imaging, it has even ways of seeing around corners or seeing through clouds. GPS, as I said, works on the idea that there's clocks in space. So when you are at home and you take out your phone and ask where you are, essentially by opening up Google Maps, you're asking different satellites where they are and what time they are. And so they broadcast the time. They're all different distances away from you. On your phone, it knows where the positions of the satellites are at that particular point. And then by measuring the time delay, because the speed of light's a fixed number, it travels at 300,000 kilometers per second, you can calculate using sines and cosines how far or what position you are with respect to those satellites. And that gives a unique point on the surface of the Earth. And to this to work, we need to measure to tiny, tiny fractions of a second. We're talking out to the 17th, 18th decimal place. Now, quantum technologies, the first transistor that was developed, when I talked about semiconductors beforehand, was something about the size of my hand. And that took over from what were known as valves beforehand, glass handmade devices, till now we have computer chips, as you are very familiar with. And what quantum technology is trying to do is get away from the system that I showed you at the start, where we have this bench weighs a couple of tons and we have vacuum and lasers and all the rest, to make something that is a chip scale device that is scalable. And to hammer home again, if we can make these things work, and we are working very hard in it, you get better timing, better center, better navigation, secure communications, and even quantum computers. I started looking through this slide, and updating it is looking at, well, why would you be interested in quantum technologies? And one of the reasons you should be is that there are fascinating jobs in this area. So this is a list of some of the companies, a small selection of companies that are working with Strathclyde and Glasgow University and other places in Scotland. And putting this list of companies together, the ones that are circled here are all companies that are based in Scotland, the Central Belt area. And I'm sure I've left out many, many companies, and I'm sure I'd be happy to add those in as well. But Scotland and Glasgow and Edinburgh and other areas are leading in this development of quantum technologies. They're world leading in development from universities of Glasgow, Strathclyde, and all the other places around Edinburgh, Heriot Watt. I'm going to leave some people out, so I'll stop talking at that point. My point really here is that it is important for the country, it's important for the economy, and it's an exciting time for what changes can happen by these quantum technologies, about developments for jobs, development for society. Let's go back to that first. We're going to finish up here shortly, which Kelvin again was reputed to have said there's nothing new to be discovered in physics. Now, actually, he didn't say that one. That was someone else at a speech, and it's one of these things that has been reported, and Kelvin doesn't have a Twitter account to disagree with it, so I would like to correct that. He never said that. What Kelvin actually said is physics is at present obscured by 2 clouds. Those 2 clouds he didn't know about were relativity and quantum mechanics. And Kelvin was aware of this. We are very good at measuring things, and he said that things like this ultraviolet catastrophe, that's where the interesting physics is. And the bits where we don't understand is where things get complicated and get interesting. And we'll finish the very last slide with this guy, Niels Bohr, who's developed the first real theory of how the quantum atom works. He said it's very difficult to make predictions, especially about the future. What I do think is that quantum technologies are a very exciting area, and there are a lot of opportunities. It's a very interesting area to work in, a very interesting area to research, and there are a lot of opportunities going forward for further research and for jobs. Okay. Thank you very much for your attention, and if you have any questions, I'm sure we can deal with those through the normal channels.